So last time what we did, we looked at the large signal behavior of a bipolar differential pair. I mean, we looked at the concept of differential pair and differential signaling, and then we got also looked into that specific kind of amplifier. The point of a differential stage, if you want to think about it, was to create a stage that not only amplifies the differential signal, meaning the difference of the two signals, but also preferably attenuates or amplifies at least less the common mode. So you want to have different gains for the symmetrical and anti-symmetrical mode, because if you have two arbitrary voltages, you can always write them, as we saw last time, you can write them as the sum and the sum part, the common mode part, and the differential part, right? So there is a common mode, which is the symmetrical part, and that's the part we are trying to suppress. And then there's a differential, which is the anti-symmetrical signal, and that's the one you're trying to amplify. And we saw that actually there was a very, in my mind, it is simple but clever technique or trick that made that possible. And that was the addition of that current source in the tail of a differential pair. You have two amplifiers, you have two common source amplifiers, and instead of having them connected to ground, you have them share the same current. And what that does is that in the case of a common mode perturbation, when the signal goes up and down together, since the sum of these two currents have to be equal, that will not induce any change in the total current, right? If you say these two, and if you keep it symmetrical, let's say they are perfectly matched, say the current through these two branches have to be equal, and their sum has to be constant, therefore they're not going to change, right? That's a trick that was actually introduced in vacuum tubes first, and then it was borrowed by transistor circuitry. Anyway, so what we did, we looked at an amplifier, and that basically led to this kind of a state. So let's say we are talking about BJTs, or bipolar transistors. So we saw that you had the two common emitter stages, that instead of being biased to ground or biased with a fixed resistor, they were biased ideally with an ideal current source. Of course, there's no such thing as an ideal current source, so there's some sort of a resistance here, and that would limit how much of this common mode rejection you will get. But in general, if you have V in plus and V in minus, or VI, say VI, yeah, VI plus and VI minus, and VO plus and VO minus, then you have basically a differential gain in principle if you design it properly. Now, another one of the considerations that we had for this is that you have this, and we wrote a large signal characteristic, right? And when we did that, we are not going to do the derivation. We saw that we used the exponential behavior and used the inversion, and we wrote it as such. And then eventually what we got the delta IC, which was the difference between IC1 and IC2, became alpha IEE, and this is assuming that this REE goes to infinity for here, hyperbolic tanh of VID, or you can call it delta VI, or VID, divided by 2VT, where VID was defined as VI plus minus VI minus. So we saw that we had hyperbolic tangent, which came from the exponential, right, when we solved that. And what it looks like, if you look at that, that characteristic, we know how, so this is VID, and this is delta IC. We know that tangent looks like this, essentially. So it asymptotically reaches alpha IEE, or negative alpha IEE, which basically means that the current of one stage is almost zero, and the current of the other stage becomes the maximum current, which is this IEE times alpha of the transistor, right? So and this is what's switching. And it happens, obviously, in this expression, you see that the stage never completely steers to one side, right? Because this is an asymptote, right? So this asymptotically reaches here. So it never quite gets there. But for all intents and purposes, once you get past 3 to 4 VTs, right, this stage is practically off because most of the current, let's say 3 to 4 VTs, and VT meaning KT over Q here, which is basically at room temperature 25.8 millivolts or 25 millivolts, 26 millivolts, whatever you want to use. Something around 100 millivolts switches the state completely. And because this current handling GM of the bipolar transistor is high, this was actually the basis for one of the fastest gates that was designed, which is called ECL, emitter coupled logic. You can use this differential switching and then drive the next stage with that. You need some sort of a follower to keep the levels constant, et cetera, et cetera. But that was used, and for some period of time in the 70s, late 60s and 70s, they made some of the fastest supercomputers of the time with these stages. Then CMOS came and blew them out of the water. And the main reason it could do that, there was one primary reason when these were displaced with CMOS gates. You're familiar with CMOS inverters, right? I mean, so the basic inverter stage of an NFET and a PFET. Well, I have to do one or the other. Okay, so let's put it this way. If it's digital, I will treat it that way. This stage, right? This inverter. This has a fundamental advantage over that as a digital block. So what happens with digital? The digital power scales with what? One is the switching speed, but also there's another thing that even is more effective and more practical. If you have two chips, one is a lot more powerful than the other one. Let's say they're running at the same clock frequency. What is the thing that's different about the more powerful one? Number of gates, number of transistors, right? So now, what is the problem with this if the number of gates increases? This guy has a problem as a gate. Correct, exactly, constantly drawing current, right? It's just constant, so it is, no matter whether or not it's switching, it's just drawing current. Now, if you're making a small number of gates, this may be okay. If you're making billions of transistors or billions of gates, then this is completely out of the question. Because when you're talking about billions of transistors, even the leakage current of this can become a significant problem. A nanoamp times a billion is 1 amp. Just so that you can think about the scale of things, right? So anyway, but anyway, as an analog stage, as an analog gain stage, it's still quite valuable. So these stages are powerful for a variety of reasons, and we'll see their power as we go. So we need to understand when something is useful and not is dictated by the way it's used. There's nothing fundamentally better about one kind of transistor or another. I mean, well, there's some transistors that are terrible, but at least the MOSFET and bipolars are, there's nothing fundamentally better about one versus the other. There are some properties that are different and they can be used for different things and more useful, or a combination of them. So that was the BJT. So let's do we are going to do a similar thing for MOSFET and write it down here. So, but before we do that, so we are going to do a similar treatment. So if we wanted to make the same stage, we know how to do it, right? I mean, it is essentially the same topology. You could make it with vacuum triads as well, if you wanted to do, and you're going to do it with the ATDs, arbitrary three-terminal devices. So if you have an ISS here, and then you have your V in plus and V in minus, and VO plus and VO minus, and then you have RD because they're connected to the drain, and VDD as opposed to VCC, ISS instead of IEE. You can have the resistor, RSS, but essentially it's the same thing. Same topology, that's what we call it, right? But it's implemented with a different kind of transistor. And this is an NMOS version. If you wanted to have the PFET version, how would that look like? Just as a side note, just for now, just to briefly talk about it. What should I have here? If I wanted to have there's a complementary, there's an inverted version of this thing, right? With NPNs or PFETs and all those things. And it would look like this. So think about how we are going to invert the stage. It's going to go like this. These are going to be PFETs. Then it's going to go to RDs, because these are still drains. And this is going to be the output voltage. These are going to be the input voltage. So this is the inverted version of this thing, flipped upside down. When you flip it upside down, you have to think about the direction of the currents and the polarity of the transistors you use. So these are both valid stages. We'll analyze this, but this, whatever we do is applicable to this. This could be also bipolar. You could do the same thing, turn this into PNPs. Okay? So I'm going to erase this. Is everyone okay? Everyone taking this down? So I'm going to start. And this is a good exercise to remember every stage and think about how to invert it. There's an inverse to every stage in this sense, right? Or flipped version, upside down version, probably even better. So we are going to do the same analysis, similar analysis that led to this for the MOSFET. But before we do that, and that would take another whiteboard, so we'll use that next whiteboard for that. But before we do that, let's talk about the ATD, arbitrary three-terminal device, right? So we can make a three-terminal ATD version of this thing, right? So this would be our two ATDs, arbitrary three-terminal device. So this is connected to terminal 1. So it would be I11. It would be R11. This would be R2, R2, V22. This is terminal 3. This is VI, and this is VO, right? So VI plus, VI minus, VO plus, VO minus. And let's see how an arbitrary transistor, what can or cannot be said about the arbitrary transistor. You will see that you can't go as far as when you knew the exact behavior, the exact functionality. But let's see what we can say. So one of the things that this does from a large signal perspective, right, we have two currents, if you think about it. There is this I1 and I2, right? Or I plus and, let's call it I2 plus because it's going through terminal 2. I2 plus and I2 minus, right? These two currents. And what we are interested in really is what we call the delta the difference, delta I. So there's a delta I, that's I2 minus I2, or I2 plus minus I2 minus, the difference current, similar to this, right? And then we also know something else, that we know that the sum of these two has to have some sort of a relationship to this tail current. Now, if for this device to be a meaningful device, it has to have some sort of a kind of like relationship, some sort of a close relationship between the drain and the source, right? So we put some sort of an alpha there, equivalent of, think about it as a transistor. So there's some sort of a taxation going on here of this tail current. What's one fraction of it? And I'm assuming that R11 is pretty large right now. So here assuming that R11 is large. So if you do that, then you have these two expressions. Then you can express, actually using these two, you can express I2 plus and I2 minus in terms of those. So you can say it's alpha I11 plus delta I over 2. And I2 minus, if you solve for these two, you will see that I2 minus is alpha I11 minus delta I over 2. Okay? So now what? What can we do? Is there something we can do? So let's write this expression. Let's write what we are interested in. So we knew that before, that the relationship describing this device, we said in general, I2 was F of V31 and V21. This was the controlling terminal, right? VGS, equivalent of VGS or VBE. This is the output terminal voltage to the input, right? VCE or VDS. This is like this comes into play through early effect, channel length modulation. And this is basically where the fundamental transistor action comes from. So let's just ignore this for a second. So let's say assuming that this is only a function of V31, the input control terminal for now, right? And let's see what that gives us. So let's say we are writing it in that form. Now, if we do that, and then of course V31, the the voltage between this terminal and that terminal, is going to be F inverse of I2. Right? It's a function, right? Like if it's a function of one variable, I'm approximating as a function of one variable, I can invert it. Now, then what we know is the following. If you look at the input differential voltage, let's say VID, or delta VI, right? I don't know, what did we use? Just so let's say delta VID, or delta VI. Delta V. Did we use VID? Here, wait, let's use VID. VID is what? Is obviously V31 of this transistor, let's call it V31 plus minus V31 minus, right? It's this voltage minus that voltage. That's the differential input voltage, right? Do you agree? It's a KVL, right? I mean, basically it's the difference between these two voltages, which would be this minus that. Think about it with this minus that, this minus that. Okay, good. So if you write it that way and use this inverse, then basically it becomes F minus 1 of I2 plus minus F minus 1 of I2 minus. What we are looking for is a relationship between the delta I, this parameter, and VID. And in this general form, I don't think you can go much farther in a meaningful fashion in general. So this is where the actual functionality can come to play. And you will see when we do the MOSFET version, there are tricks that we are using to, for example, in the bipolar case, we use some properties of the exponential, right? We factored half of the exponential out so we could actually play with that. And we see here we are going to play with the properties of the quadratic. So that's where the actual functionality will come into play. So if you have an arbitrary device, you have to really look at that functionality. Now, let's say 20 years from now, you're working on this new device you've invented, and you've done some basic measurements of that, and you want to see some properties. You will see that some of the properties are independent, especially when we get to the small signal properties. You can actually derive it from the curve. One thing, but if let's say you're somehow interested in some large signal properties of this thing, one of the things you could do, you could try to curve fit some function that's relatively easy to play with. And it may not be exact, but it may be simple. And when you do that, it allows you to derive some relationship that you know is approximate to begin with. Even this is approximate. Because there were a lot of approximation that went into equations that we used to make this. So anyway, if you need that, you can make a closed form. Or you can say, this is the functionality, this is the curve, this is the behavior. But that's basically where you kind of like need to do something. But now, one thing we could do here, though, is the following. We could say, OK, fine. But what if let's say I try something here. There's a little step that I can take, which may have shed some insight on this. So let's say if I divide both sides by delta I. OK? What do we get? You get F minus 1 of I plus I2 plus minus F minus 1 of I2 minus divided by I'm going to expand the delta I. I2 plus minus I2 minus. What does this remind you of, this form? It should remind you of something. Derivative, right? In fact, if the difference between I2 plus and I2 minus is small, this is indeed the derivative. So I would say approximately for small, so I can say delta I going to 0, then it becomes exact, is the derivative of, let's say dI of the F inverse. And just for the sake of, just for the heck of it, let's see. Let's do it for this function. Let's pick one of the functions we have already looked at and see what we get. Okay? So let's pick that one. This is an example. Okay, I'm running out of space. I'm going to put it here, do the calculation here, and put the result there, because then we can get rid of it later. So we're going to start here. I'm going to encroach on this guy and borrow from it and give it back later. Okay, so what is that function? So F, we know what F is for bipolar transistor, right? Because we know IC is IS x e to the V BE over VT, right? But we are interested in the derivative of F inverse, right? What is F inverse? F inverse is VBE equals VT natural log of IC over IS. So we are differentiating that with respect to IC. So what is the derivative of this thing? So it's VT. It's the derivative of the ln, natural log. What's the derivative of log, natural log? 1 over the argument, 1 over the function. So it would be IC, and then it would be IS, right? Times the derivative of the argument, which is IS, right? No, that, I'm not times that, right? So this is the derivative. If this was u, right? It's 1 over u, and then this is du, di, right? So these two cancel. You're right, but that's because. So what is this? Rm, or 1 over gm, right? This is Rm or 1 over gm. So Rm 1 over gm. So it says the relationship, if you do the derivative, which for example BJT, then I guess it should be delta V really. I mean, let's change this to delta Vi, because then it makes more sense in terms of the notation. Delta Vi, make this delta Vi. And then it would be delta Vi over delta I would be Rm, or 1 over Gm, which makes sense, right? So the rate of change of that current at the output is proportional to the Gm of the transistors. So it's an example. And then you can do it for anything. So you can see this is true for anything, actually. But keep that in the background. Whenever you're dealing with the differential pair, this is what you're doing. Now, this step going forward from here in large signals, sometimes you can actually go further depending on what that function is. If you had a velocity saturated device, this would be linear, deeply velocity saturated, and this would become very easy, because this would be proportional to delta IC. And then you can solve it by dividing for delta IC, dividing by whatever that proportionality constant is. Anyway, all right, so let's go back to this guy, to the MOSFET, and then do the analysis. This is, again, these are a little bit hairy because you're looking at the specific functionality, but it's okay. I mean, we do it once so you can see how they look like, and then you can use it whenever. And there's some useful insight that comes out of it, as we'll see. Okay, so let's do the analysis. Let's go through the MOSFET thing. So what we do for the MOSFET, again, I'm going to redraw the stage here so we have a reference point. ISS, and then you have the Vi plus Vi minus, you have the Vo plus Vo minus, Rd, VDD, okay? My right-handed transistor come out differently from my left-handed transistors because of the way I draw them, but anyway. So here's the thing, look at them and look at this, and what do we know? We can do the same thing. We can say, okay, well, there are two things. What do I know about the transistor? First of all, I have to know what set of equations am I using. What region of operation am I in? So that's a good question, right? We should have asked that question about bipolars too. BJTs when we talk about what region of operation are we in? Is the transistor off? Probably not, because you have a current source forcing current through it. So the transistor is on unless you kind of like do something fun. If you had an ideal current source, this transistor was forced to be on. So it will adjust this voltage. So you may say, oh, I can keep this off. I can put this at negative 10 volts, these gates, and the transistor will turn off. No, if you have an ideal current source, this would go to negative 11 volts and would keep them on. because that's an ideal current source. Well, you don't have an ideal current source. That current source can crunch, and then the stage can actually turn off if you didn't have an ideal current source. Because now if you have one made out of transistors and you pull this down to negative 10 volts, or if this is 0, let's say, negative 10 volts or negative whatever, then you can turn them off, and nothing will flow. But if you, let's say, so the transistor with an ideal current source is on. And this is the distinction you need to make between real and ideal stuff. So, okay, so it's on. Now, what region of operation? Are we in triode or pinch off? And how do we know? Is there any guarantee that we'll be in pinch off? No, right? So if you design this poorly, you can force it into triode. What is poorly? Well, what is this voltage drop, right? And what is this voltage? That determines if you're in triode or pinch off. Because you want this voltage, the VDS, to be greater than that delta VGS, VGS minus VT across here, the gate overdrive, the excess above VT. Right? So you want this to be greater than that. So which means that what's the maximum current that can flow through this RD? What's the worst case scenario for how low this voltage can be? Think about that. Right, one of the transistors is completely on, all of the current is going through one side, so this becomes ISS. So the maximum voltage drop across this thing is RD-ISS if all of the current goes one way. So the minimum voltage here is going to be VDD minus RD-ISS. Right? And as a result, as long as your input voltage is designed such that it's, when you calculate the VGS minus VT, this is not, basically, as long as this is no more than VT above this voltage. If your gate voltage is no more than a VT above the drain voltage, this transistor is going to remain in pinch off. So you have to guarantee that condition. The same thing is true for bipolar. It's not automatically true. So you can't put just like, if I put a 5 mega ohm resistor in the load, just like an actual resistor, and I have a tail current source of 1 milliamp, what is 1 milliamp times 5 mega ohm? 5,000 volts. So obviously the transistor will go into well, a bipolar transistor will go into saturation, a MOSFET will go into triode. Okay? So that's something to keep in mind. But now let's say we've designed it in a way properly that it doesn't enter triode. The input voltage, and this is something we need to be mindful of when we design. If you design it the wrong way, it's not going to do what you want. Right? So anyway, so let's say we are in pinch off, and in pinch off we know that we have ID equals mu n Cox over 2, W over L, so these are W over L's of these transistors, VGS minus VT squared. Now we call this whole thing for analysis not to carry it around all the time, we call it K prime. Right? So lump all of those parameters into K prime, and then at the end we unpack it. So this is basically K prime VGS minus VT squared. Or, now what I need to also know the inverse function. We are going to be using the inverse function, right? We know that already. So let's invert it. So inverse or conversely, VGS is VT plus square root of ID over K prime. That's the inverse function. Right? You can easily see it. Now, okay. So what we are trying to calculate is those parameters, delta I, which is ID2, ID1 minus ID2, right? And then we have, and we know also that ID1 plus ID2 is ISS. Alpha is 1 in the case of MOSFET, or classic MOSFET. And then we take these two, you can write them in those forms. So basically that would give you ID1 equals delta I plus ISS divided by 2, or ISS plus delta I, let's write it that way, because it makes the other one better or easier to read. ID2 is ISS minus delta I over 2. Okay? So 2 equations. Now, what we are trying to do is to calculate the VID, or delta VI. Right? So from this, you can say delta VI, or VI is VGS, oh, this should be capital, VGS1 minus VGS2. Okay, so I plug these things in. So it becomes VT plus square root of ID1 divided by ISS minus VT minus square root of ID2 divided by ISS. Right? So can I simplify it more? Can I cancel the VTs? Yes? No? Be careful. Math and physics are two different things. Whenever math shows you something, you have to understand the physics of it. So is it true that I can cancel these two VTs? What are the assumptions behind it? You have to always investigate these assumptions and think about them. So a couple of things. What do you think are considerations that I have to think about? At least, I mean, some of them may be important, some of them may not be. But what would you worry about? If I say, now that I've kind of raised your sensitivity to this, say, well, it's VT minus VT is 0, right? So, well, this is the VT of this transistor, this is the VT of that transistor, right? What are some of the considerations here that you need to think about, which will have impact? Some of them do and some of them don't, but have impact on design. So what are the things that we should worry about?
They should both have the same voltage.
They should have, why the same voltage? What?
If you shift the voltage, it changes the depletion of each edge.
Right, so that has a name, right? Body effect, right? Right, correct. So the body effect, which basically is a change in the threshold due to the difference between the source and the bulk voltage. It turns out, actually it's a very nice coincidence really, that here if you think about the body, the bulk is connected to ground, and the two sources are connected to each other, so they share the same VBS. So actually body effect doesn't change the threshold. So in this analysis, you have not ignored the body effect. The body effect naturally cancels because of the operation of this transistor, the way it's connected, because of the topology. Right? So body effect is not ignored. It just doesn't enter the equation because the source voltages are the same for both of them. So VBSs are the same for both of them, which is what controls the threshold voltage. Yes, they change. They're functions of the source voltage, but they change the same way. So you still can cancel them. So this is the function of VBS, and this is a function of VBS. But they're a function of the same VBS. So that part, the body effect is good. We are good with that. We don't need to make any assumptions here. We are not. But can I cancel them now? Temperature. There may be difference between these guys, right? So if you wanted to minimize that, what would you do? How would you make sure that the temperature difference between these two is minimum? Make them as close as possible, right? So that's one step. But we are not completely done with that. We'll come back to it. What else? What else? What are the other considerations? Yes, Dave?
You can ensure that they're connected by some sort of thermally conductive material.
Sure. I mean, that's to deal with the thermal, yes, the thermal conductivity. By the way, just so another piece of useful information. Silicon is an incredibly good thermal conductor. It's 4 times better than brass as thermal conductivity goes. That's actually a very nice property of silicon. So the it facilitates your thermal design. Oh, for better or for worse, it may actually, depending on what you're trying to do. If you're trying to create thermal isolation, it's not a very good material because it's highly conductive. So anyway, but going back to this question, what else, other than temperature variations, temperature differences, can affect create a mismatch here? Did I make a mess? By the way, I have made a mess here. So this needs to be corrected. These are K primes, not ISSs. But anyway, correct those. I wrote this as divided by ISS. It should be K primes. Yes?
Tightness of the fabrication.
Yes, tightness of the fabrication. We refer to it as mismatch or matching properties. Yes, that's exactly what you referred to. That's correct. You make two devices that you want them to be identical, right? If I make 2 copies of something, depending on how tight I can control my fabrication, or how tightly I can control my fabrication, they may not come out exactly the same. So your W over L's may be different. The shape of the device may be different. The gate oxide thickness may be different. So that would change other parameters, mu n, C ox, W, L, etc., etc. There are other systematic variations in the process. What do I mean by systematic variation? When you make a big wafer, when you're doing implantation, for example, across it, or you're doing thermal processing, the stuff in the middle of the wafer are a little bit different from the stuff that happens on the edge of the wafer. So if this is the wafer, there's kind of like gradients. There's the lines of equal, so there's gradients outward for the device. So there's variations in different directions. So if a threshold adjusted here may be different from the threshold from here. There's also random fluctuations, but there's some systematic process variations. So how do we deal with these things if we want to have really ability to cancel these things? So that's why it's important to think about equations as you write them. Don't just like write equations. What am I doing? Okay. So how do we get around that? So let's say we want to deal with this issue. There's a gradient. There could be a gradient in certain direction in the variation of the parameters. Is there a way to minimize this effect?
Source them from nearby points.
So nearby points again, okay? So you can put them as close as possible you can. So that's fine. How about this trick? Let me ask you a question. So what if I put two of them here, right? I put them vertically, like that. The two transistors. So those are the two transistors, let's say. Would that deal with the gradient issue?
If it was purely radial, yeah.
Would it deal with all of them? Right. You don't put the design radially, right? You put the design, you have a square grid. Exactly, right? So yes, it works here, but is it good here? Because you can't say, just turn these, right? It's very nice here. It's awful here. But, good ideas usually are generated from different pieces of bad ideas. So if you have an idea, maybe you can say, well, it didn't work that way, but can I play a trick on this? Can you think of a way of using this concept, this core concept, and that, as we will see, it will also help with the thermal as well, to overcome this problem or alleviate it, or use this concept. Obviously, this didn't work, right? Because, yes, it works nicely here, it works horribly there. What would work there? What would work up there or down here? This would work down here, right? Can we think of something that would do that, at least to first order?
You can split up your transistor in a sense.
Uh-huh.
Put different pieces of it, and you can kind of crisscross and then maximize that if the gradient is coming at an angle, you get high, low, slow, and then medium, medium.
Exactly. So that's a very good point, right? He says, okay, instead of making your transistor as one piece, make it a two smaller pieces. So I'm going to magnify this picture, right? Instead of having a transistor, so there are multiple fingers probably, or long, you don't do it as one long finger, right? You just, if you have like a W over L of, let's say if your W is 100 microns, your L is, quarter micron, you don't make just one giant finger. You make it out of like 50 or 100 or 10 fingers, we call them fingers, gates, and they put them in parallel. So you make 10 smaller transistors and put them in parallel. So split your transistor. Put half of the W over L here and half of it here. So let's say this is transistor 1, M1 and M2. And then what he was suggesting is that make the other half of M1 here, let's call it M1 prime, and M2 prime. And crisscross them. That's the word you use, right? Or cross-connect them. So let's see what this does in different scenarios. If the gradient is this way, let's say these are the equi-VT lines. So the gradient is horizontal, right? Would this work? Would this suppress it? So yeah, let's say this one will have a little bit of extra, so this would be VT1, this would be, this would be VT plus delta, and this would be VT, and this would be VT plus delta. So in aggregate, you have a transistor, the two transistors will look alike. Because each one of them is made out of two halves that are similar. How about other directions? Let's say now you're here. The gradient is going in this other direction. Let's say you're looking at these equi-VT lines. What happens to the VT? So here you have VT and VT, and you have VT plus delta and VT plus delta. Right? Are we still good? We come back and say, what if it goes this way? Where's my green? What if you're here? What are we going to get then? Let's say do we agree that these two are seeing about the same thing? Let's call that VT. What does this one see? VT plus delta. And what does this one see? VT minus delta, right? But you have two VTs, and you have a VT plus delta and VT minus delta. Now, you could argue, say, well, if it's quadratic, how is it canceling? Well, it's better than no cancellation, right? It's a first order cancellation. This structure is very common when you're trying to match devices. It has a name. It's called common centroid. But you understand how it works. Same thing with thermal, though, right? Same thing with thermal. Noah.
So the circuit has two transistors, and then you said that each of those squares has like multiple.
Right. So think about this as if this was W over L, right? So if can I make a transistor of W over L? Is it equal to two transistors, each one of them with W over 2L? Well, that's not the right way of writing it, because that implies something else. W over 2 over L, W over 2 over L in parallel. So that's what these combinations are. These two are these two. And these two are another pair of that are connected that way. So there are considerations in the design. In fact, you could think about it, can you do a second order cancellation by making a larger number of smaller fractions and connecting them in an interesting way? Or higher order cancellations. And there are interesting things you can do there. But just think about that. But this is the concept. So yes, you see something that doesn't work, don't just dismiss it. You may be able to use it. We used it twice in opposite direction. And that's how we arrived at that, right? Make sense? All right. So good side discussion, important discussion. Let's go back to our calculations. So subject to all those assumptions of matching, now we can say, okay, so what do we get? Well, we have 1 over square root of k prime. And I can write these things in those forms. So I can write it as ISS, or I can factor that 2 out, ISS plus delta I minus square root of ISS minus delta I. I'm just plugging these things in. And I factored that 2 and square root of k prime. By the way, that factorization also is subject to the same assumption. I could not do that factorization of square root of k prime if the devices were not matched. Because they are different mu and c ox over w over L's. The mobility of the channel may be different there because they implant. The crystalline structure may be a little bit damaged there. The oxide thickness, the gate oxide thickness may be different from one transistor to another. The W over L, these are what you drew. It may not have come out exactly in the lithography process. They may be different. So this factorization, which mathematically is obvious, physically may not be correct. Always think about what's happening there. All right, but again, subject to matching. So that's what we get. So that's delta VI, right? That's delta VI. So we got an expression like this. What do we do with it next? So let's take the next subsequent step. So what do you think we should do? what we need really is an expression for delta I in terms of delta V. So we are trying to solve for delta I. So from here, it's basic algebra. Right? What do we do? Algebra. What do we do? Can you suggest a next step? We're trying to solve for delta I in terms of delta V. Well, you're dealing with square roots, right? Square it. See what happens, right? So if you square this, what do we get? We get delta Vi squared is 1 over 2, well, let's put this on this side for now, 2k prime. And then on that side, what do you get? You get this squared, which is what? ISS plus delta I plus this squared, a minus b squared, right? ISS minus delta I minus 2 times the product of these two. It's a plus b times a minus b under square root. So it's a squared minus b squared, right? So it's ISS squared minus delta I squared, right? Agree? So, and then this cancels that. Oh, no, that doesn't cancel that, sorry. This cancels that. And this becomes 2ISS, so I can cancel this and write 2ISS. So there's a 2 on everything, so all these 2's cancel. So what do we have here? And then I can move this term to the other side and keep the ISS here, so we get square root of ISS squared minus delta I squared equals, we move that one here, so it's ISS minus k prime delta Vi squared. So that's what we have so far. We're getting closer. We still need to solve for delta Vi, but it's trivial now because we have only one delta Vi. So we square it again. Okay. So we square it again, we get ISS squared minus delta I squared equals this thing squared. So let's square it. It's ISS squared plus k prime squared delta Vi to the power of 4 minus 2 times k prime ISS delta Vi squared. And these guys cancel again. So now you need a minus sign. Okay, fine. So basically you can write this as delta I equals, so it becomes this minus that. You can take a square root, so you can basically write as k prime delta Vi times square root of, so it would be whatever is left of that, which would be ISS over k prime minus delta Vi squared. Double check. Yeah, oh, and of course there's the 2 here that I left out. This part is algebra, right? Okay, fine. We wrote the algebra, we derived it. Let's put it down here. So what we have here is delta ID, or delta I, delta ID, let's call it, is k prime delta V square root of 2 ISS over k prime minus delta Vi squared. All right, how does this look like, this expression? Well, if delta Vi is small, right, this term would be small, so this would be dominated by that term, so it become proportional. You get that kind of behavior, which makes sense. So if you try to plot delta ID versus delta Vi, delta Vi. Here, what you have here is that in the beginning, there's a fixed slope. And that slope is GM, essentially, right? We already know that for anything. But then this starts slowing it down. As VID stops growing, it makes this factor smaller and smaller, right? So it starts doing this. And if you go according to this equation, what it does this till this becomes equal to that and becomes 0. It's quadratic, essentially it's a square root thing. So then it just, does that really happen? At this point, already, what you have is the point where all the current is steered to one side. So the other transistor is already off. There's no more current to provide. So if current really saturates, this does not happen. So this equation is valid because of that, only to this point. Because that transistor carries no current. Because algebra allows for currents to be positive and negative. But the device physics does not allow the drain current to be going in the other direction, at least not under the similar conditions, right? Because if it was going in the other direction, that means that it was the source, essentially. It became the source. You flip the terminals. So practically, this equation is valid up to here when one of them turns off. So the question is, where is this? What is this voltage? What is the voltage at which one transistor completely switches? We talked about this kind of say, well, there's no voltage like that for BJTs, but there appears to be one for the MOSFET, exact voltage. So at the point where it's completely switched, what is this current? Just at that point, what is this current? Let's say it's switched completely to one side, to the other side, I don't know, to this side. Let's say all of the current is going through here. So this is ISS. And therefore this current is 0, right? So according to our basic model, when the current is almost 0 or negligible or infinitesimal, what is the threshold voltage? When you just get there, when you're just arrived at the verge of that, what is the threshold? What's the gate voltage? What is the gate source voltage? The threshold voltage, right? I got a Freudian slip. Okay, so it's the threshold voltage, right? So when this is VT, at that point, this is VT, and this is some VT plus some delta VGS, right? Some gate overdrive. So the differential voltage that induces this is the gate overdrive when all of the current is going through here, because it's this voltage minus that voltage, right? So it's delta VGS. The differential voltage of delta VGS would do that. Now, if you think about that, what is that voltage? Well, it's relatively simple to calculate. If you look at it, it's basically K prime delta VGS squared has to be what? ISS. So delta VGS is ISS over K prime squared. I'm sorry, square root. So this is delta VGS for switching. So this is essentially the threshold of switching. So this is basically ISS over K prime. And here's minus square root of ISS over K prime. So there's a voltage at which, based on the simple model, the current is completely switched from one side to the other. Now, if I tell you that in reality, it really looks like this, and ask you why, what is the response? Subthreshold current, right? So when you get to subthreshold, you're looking more like an exponential, you're looking more like a bipolar. So yes, you get very close there, but you don't quite get there in reality. Does it matter? Well, it depends on what you're doing with it. If you're using it as an amplifier, where do you want to prefer to where do you prefer to use it? Which area? The middle, right? And here or there. If you're using it as a switch, you're switching current back and forth, and if your switch can handle a little bit of a residual leakage current, fine. It doesn't completely switch, who cares? I'm getting 99.9% of my current from one side and 0.1% on the other side. If you're trying to do something precision that requires this to be 0, then it matters. So you can see these parallels, right? I mean, you can see that they are very similar the parallels are quite similar, and they tell you quite a bit about it. So this is the large signal part of this thing. And it's interesting because let's talk about a little bit. Large signal also tells us something else, a couple of other things. So we talked about this range of operation. We say, okay, if we wanted to switch quickly, we want to switch. So this switch is over 100 millivolts, and this switch where it switches, it depends really on your design parameter. It depends on your mu and Cox, and it depends on your W over L, and so on and so forth. So for example, let's say we want to extend this range. Let's say this range, you come back and say, well, what? 100 millivolts for what I'm trying to do is very small. I want to extend it to 1 volt. What do we do? What did we do with it? You remember? These are essentially common emitters, right? And we'll see them even more clearly when we, like within a few minutes, when we do the small signal half circuit models or half circuit equivalents. But this is right now, let's say for this thing, if I wanted to extend, if I had a common emitter, how would you extend the range of a common emitter? Emitter degeneration, right? So where should I, okay, so what happens, forget about this for now. Let's say, so would this be a good way of doing that? Okay, some of you are tentatively shaking your heads, which is good. There's something wrong with that. At least the way I asked it should be, there's something should be wrong with it, right? But what is wrong with that? Does that do anything? No, it's a current source in series with a resistor. It's the same current source from a circuit perspective. This does nothing. I mean, if that were an ideal current source, this would do exactly nothing. I mean, of course, there are no ideal current sources. That's why I removed that to make it simple. So that would do something, but it's not a good thing anyway. So what do we do? Are we done? This is not the way. That's not where you put the resistor. But where would I put it? Yeah, you're doing this, which is good. Like one each on each side. So what if I put an RE here and RE here? And we will calculate what the gain of these things are soon. But what does this do? So now your differential voltage gets divided between the VBE and these. The differential voltage is appearing across here. So it's going across here, right? So now it sees the VBEs and it sees these REs. And that's why that other thing didn't work, because the differential voltage doesn't see it at all. The differential voltage still sees the two VBEs back to back. Now the differential voltage sees these things. And again, this becomes more pronounced when we talk about half circuits, equivalent half circuits. But I want you to get a feel for it. But anyway, if you introduce an RE, then you can expand this. So you can actually make this wider, going through the origin. All right, something like that, right? How would you do that on the MOSFET side? What's the best way of doing this in the MOSFET? Well, you can still do the same thing. I mean, you can put an RS in there. But if, let's say, resistors were expensive, can you think of a way of expanding this range without putting the resistor there? What is, yes? Sorry? Change the current source here? Yeah, I mean, if you change the current source, basically you're changing this because ISS is going down. That's fine. That's definitely a valid answer. But let me just add another constraint to instigate other answers, which is actually sometimes true, is that let's say you need to operate with a fixed amount of current because of frequency response things we haven't talked about, or the swing or the drive capability of these things. You need to maintain a certain amount of current to either be able to drive or to be fast or both or something like that. So let's say your ISS is at whatever the minimum it can be. But generally, you don't want to be operating at the maximum it can be, right? Because it consumes power. So let's say that was a valid answer. What else can we do? What can we do? Yes, how can we change K prime? Correct, we need to change K prime. We need to make K prime larger or smaller? Smaller, right? So can we change the mobility of the electron? You can do play tricks, but that's more of a device solution, not a circuit solution, right? I mean, you can strain the silicon, you can do things with doping, you can change the materials, things like that. Same thing with COX, right? COX is, yes, you can try to make, but this is something that involves billions of dollars of investment in, and I mean billions in plural, tens of billions possibly, of investment in a new foundry or new line in a foundry with something. So let's say you're in the context of your little startup that we talked about a few lectures ago, when we were talking about the economics of the thing, and you can't do that, or you don't want to do that, obviously. There may be some simpler solutions. Obviously, there are some other parameters here, right? 2, I don't think we can change that much. It's hard to change that. So what else is left? These are design parameters in MOSFETs. You should think about them as design parameters, W and L. Right? So what do you want to do? You want to make it W over L, small or large? Small. But that also goes into, that's in conflict with something else. Because if you remember, what is the transconductance? The expression for transconductance, both expressions had W over L in them. Whether if you're operating at constant current or constant voltage. In this case, you will be operating more close to constant current because your total current is fixed. So you have a square root dependence on W over L. You make your W over L smaller, your GM goes down. Your transconductance goes down. And you pay the price. Your drive capability goes down. Your transistor becomes weaker. When your transistor becomes weaker, especially when you're talking about high frequency operation or driving a load, you will pay. It's not as strong to drive things. What else? So we can reduce it, yes, but there will be a price. There's a trade-off. There's something else that happens. When you make your W over L smaller, what happens to delta VGS? We are expanding it, right? But it means that there's a larger voltage you need to maintain here, which basically means that your headroom is shrinking. That's inevitable, right, in a way. If you're saying, if I'm trying to say, I want to expand my range of operation, right, you will come to some sort of a conflict eventually with some sort of a voltage ranges that you have at the rails, the supply voltages. There are tricks around it, but they're second order tricks. And we'll talk about those when we go forward, but just understanding these things. Is this concept clear? I mean, do we understand what we are doing with this? Do we understand why we are doing it? And what affects what? The same thing with bipolar transistor. The bipolar transistor, you have fewer controls over that because this current is essentially setting the GM, so you have to use the REs. Any questions on these? Good? Okay, so let's take a quick break, and we'll come back and discuss the rest.